Fourier theory is one of the more important concepts you're going to learn in this class. You could think of it as a bridge between the time domain and the frequency domain. In the time domain, we'll talk about things like sinusoids, and we'll see that in the frequency domain, a sinusoid becomes a single spike at a particular frequency. We'll talk about square waves in the time domain. And we'll see that square waves become an infinite series of spikes in the frequency domain. One of the best ways to view this is to shift over to Sonic Visualizer. It allows you to examine a music file in both the time domain and frequency domain. In this particular example, we've loaded up a file called sine wave. It has a single tone that plays through the entire clip. Here on this oscilloscope display, you can see that the waveform has a period of 1 millisecond, which means the tone is 1K, 1 kilohertz. If we play it, it sounds like this. We have time moving in the horizontal and amplitude in the vertical. This lower window operates as a spectrum analyzer. On the horizontal, we have frequency. In this case, it extends across the range of human hearing from about 20 hertz up to 20,000 hertz. If you play music, you'll recognize this as a piano keyboard. If you really know your piano, you'll recognize these grayed blocks as the note C. On the vertical is amplitude. That amplitude is given in dB. So that's dB relative to full volume. When we play the music file, we see that there's a single spike, which means a sinusoid in the time domain will appear as a single spike, a single frequency in the frequency domain. If there was any distortion, or if that sine wave was less than perfect, we would see additional spikes. We would see harmonics over in this range. There are some artifacts here, but you'll notice that they are negative 60 dB relative to the signal of interest. One more time. The oscilloscope is time on the horizontal, amplitude in the vertical. The spectrum analyzer is frequency on the horizontal and amplitude on the vertical. Sonic Visualizer also provides a spectrogram. The spectrogram has time on the horizontal. It has frequency on the vertical axis. The intensity changes based on the amplitude of our signal, but it's amplitude at a particular frequency. So if we were to zoom in, we can see that this bar right here is at 1 kilohertz. So you could say that all three displays provide the same information, they just have different ways of doing it, and each one has certain advantages depending what you're looking to do. For our next example, I've loaded up what is quite possibly the most annoying piece of music you're ever going to hear. And with that said, let's play it. Okay, glad that's over. Some really interesting things are happening here. You notice that the music changed. It started to sound different. So let's look at each piece and see if we can understand why. It started out easy enough. As with our previous example, it looks like a sinusoid in the time domain. It looks relatively clean with no distortion. In the frequency domain, we can see that it's clean. There is no distortion. There are no harmonics here at all. It's a sine wave. Here, it changes. We get this second peak of energy. So our fundamental was 220 hertz, but now we have this second frequency at the third harmonic. You can see that it's at 660 hertz. A third harmonic has a really interesting property in that if you were to superimpose them on each other, you would find out that the valley of the third harmonic occurs at the peak of the fundamental. So if you add the two together, you end up with this attribute right here. Originally, this signal went up and then came back down, but because we're adding the third harmonic, the valley of the third harmonic is suppressing the peak of that sine wave. On the other side, the third harmonic has a peak at the valley of the fundamental. So it ends up increasing the amplitude at this particular point. As we continue on, now there's another tone. This time it's at 1.1 K, which is the fifth harmonic. Now the fifth, when added to the fundamental and the third in the time domain, does this. We can see that the fifth would have a peak during the valley of the third, but the peak occurs simultaneously with the fundamental. Anyway, you can see that they have added up and we're starting to become more square on top. Same thing in the valley. You'll also notice that the skirts of this waveform are becoming steeper. Continuing on. Now we have the fundamental, the third, the fifth, seventh, and the ninth. We know it's the ninth harmonic because 1980 divided by 220 is equal to 9. Again, as before, we can see that the edge is becoming steeper and our top is becoming more square-like. In the time domain, we can see that this rising edge is becoming steeper and the top of the waveform is becoming more flat. We add more harmonics. We're about halfway through the music file right now, and we have arrived at 6380. When divided by 220, that is the 29th harmonic. And we can keep going until the very end of the file. This gives us a reasonably good approximation of a square wave. The edges are very steep and the top is quite flat. Not perfect, but pretty close. The takeaway from this exercise is to recognize that a square wave in the time domain is composed of an infinite series of odd harmonics in the frequency domain. Again, fundamental, 3, 5, 7, 9, and so on and so forth, all the way out to infinity. This is the spectrogram for our sine wave to square wave conversion. We start out way down in this corner with the fundamental tone, and then every second or so we add another harmonic. So this is the fundamental, third, the fifth, the seventh, the ninth, the 11th, and so on. We're going to play it one more time. See if you can hear when those extra tones are added. All right, enough of that. But I think you can hear it. Our next example is a triangle wave. In the time domain, you can see that it's a triangle. In the frequency domain, it appears to have the same structure, where here's the fundamental at 1,000. Here is the third harmonic at 3,000, the fifth, the seventh. The difference is the relative amplitude of these harmonics. We would find that the harmonics decay much faster than a square wave does. In a moment, we're going to shift back to the square wave. What I'd like you to pay attention to is these intensities down here. I think that's the most telling difference. You can see that the bars are much more intense. There are more orange than there were before. And I'll just switch back and forth a few times so you can see that. Triangle, square, triangle, square. Well, over here, we can look at something called a sawtooth waveform. Now this one's quite different. In the time domain, it looks like the teeth of a saw. But you'll notice in the frequency domain that there are many additional spikes. Here's the fundamental at 1,000. But check this out. It also has the second harmonic at 2,000, and the third, and the fourth. So when we look at the square wave, we can see it's composed only of odd harmonics, but the sawtooth is composed of the even and the odd harmonics, which gives it quite a different sound. Before we shift back to the blackboard, let's ask ourselves a question about bandwidth. The bandwidth of a sinusoid is very small because it's only composed of a single frequency. In this particular case, it's 1 kilohertz. What is the bandwidth of a square wave? And the answer is it's extraordinarily high, because a square wave is composed of an infinite sum of the odd harmonics. We can see that in the spectrogram, where there is significant energy, even here, in the highest frequency ranges. Fourier series is the bridge. It's a way for us to go from the time domain to the frequency domain. We saw that a sinusoid in the time domain was indeed a single spike in the frequency domain. We looked at a 1 kilohertz signal, for instance. So over here, we talked about a 1 millisecond period for a 1 kilohertz signal. In the time domain, we saw the square wave. Just like the sine wave, it had a 1 millisecond period. In the frequency domain, it appeared to be a series of spikes. We saw that those spikes were harmonics. So this one was the fundamental. We'll just call that fun. This was not the first, excuse me. This was the third, the fifth, the seventh, and so on. So the square wave is composed of an infinite sum of odd harmonics. Mathematically, we can describe it like this. F of t, which is our square wave described in the time domain, is a summation from n equal 1 to infinity of 4 by the voltage n pi, all multiplied by sine of 2 pi n f t. Make that t a little better. With the stipulation where n is an odd integer. If we expand this, f of t is equal to 4v over pi Actually, that would be 1 pi because n for the fundamental is 1. Sine 2 pi, in this case n is 1, so it would just be ft, plus 4v over 3 pi, because n is odd, so that's this n right here, sine 2 pi 3 ft plus 4v over 5 pi sine 2 pi 5, because this time we're talking about the fifth harmonic, ft, and that would continue on for infinity. This is the fundamental. This describes the third harmonic. And of course, this describes the fifth harmonic. So the things that we really have to watch out for are this F, which describes the frequency. So that would be the frequency of the fifth harmonic. And then this term here out in the weighting coefficients that describe what the amplitude of that particular sinusoid will be. Here's an example. We want to describe the first 3 tones for a 1 kilohertz square wave with a 10 volt amplitude. Now it of course would all be in the frequency domain. Here's our base equation. So we start with n is equal to 1, going all the way to infinity, because a square wave is composed of an infinite sum of odd harmonics. 4v over n pi, all by sine of 2 pi f n t. The fundamental is described as 4v over pi sine 2 pi by 1000 t. The third harmonic would be 4, whoops, this isn't v, that's not what it should be, this should be 10. There we go. So 4 times 10 over, in this case, 3 pi sine 2 pi by 3000 t. And the fifth harmonic, 4 by 10 over 5 pi sine 2 pi 5000 t. These are the frequencies, and these are the weighting coefficients to describe the amplitude of each frequency. If we were to sketch that in the frequency domain, we'll let this be the fundamental, the third, and the fifth. This would be 1 kHz, 3 kilohertz, and 5 kilohertz, with a peak, and we'll write it up here as 40 over pi. This would be 40 over 3 pi, and 40 over 5 pi. Keep in mind that there are more harmonics, and that this, in theory, extends out forever, because a square wave is an infinite sum of odd harmonics. The square wave is an infinite sum of odd harmonics. There's infinity, and n will always be odd for a square wave. You should know that there are other periodic waveforms. For example, the triangle waveform is described as f of t is equal to negative summation of n starting at 1, going to infinity, of 8 by the voltage over pi squared n squared cosine 2 pi f n t, where n is odd. When we looked at the triangle wave in Sonic Visualizer and compared it to the square wave, we saw that the triangle wave's harmonics dropped off faster. And we can see that drop off right here because the triangle wave decays at n squared, whereas the square wave decays as n. So while we describe both ways as an infinite sum of odd harmonics, we can see that the energy in the triangle wave, the high frequency energy, will be considerably less. A question you might ask yourself is, why are we concerned about this summation of sinusoids? I suppose on a practical level, we could argue that it reinforces the differences and similarities between time and frequency domain. As we continue on, the concept of bandwidth is going to become more and more important to us. If you're tracking, you might already see a problem on the horizon. We've said that the square wave is an infinite sum of odd harmonics. Our bandwidth is equal to the highest frequency, that's an F2, minus F1. We're going to run into problems if we try to write an equation that looks like this. If square waves are truly an infinite sum, that means the highest frequency is actually infinity, which means the bandwidth is going to be infinity for a square wave. Well, that's a problem because there's not that much room in the electromagnetic spectrum. So we're going to have to find some ways of filtering those square waves. In a practical example, if this is a square wave generator, we can run the output through a filter. We might run it through a low-pass filter. And what that will do is it will remove the upper frequencies. In the frequency domain, that looks something like this. If this is the fundamental, the third, the fifth, seventh, so on and so forth, if we devise a filter such that that filter only lets this portion through, for example, if this was 1 kilohertz, and we devised a low-pass filter with a cutoff point of, say, 8 kilohertz, that filter would let the fundamental through, the third harmonic, the fifth harmonic, the seventh harmonic. All of those we get through, but anything higher than that would get cut off. Of course, we'd have a problem now because the output of this filter is no longer a square wave, because a square wave requires infinite harmonics. We don't have those anymore. Instead of having a nice clean square wave with rising edges and flat tops, we end up with edges that are tilted. And instead of these nice clean transitions, we end up with things that get a little rounded off. Let's end up with something that looks like that. It's square wave-ish, but it's not exactly a square wave anymore. But how could it be? Because the harmonics, these upper portions, have been removed. Another reason for exploring the Fourier series is to simplify things. For example, we know that waveforms can be complex. For example, voice. The voice is not one frequency, but it's a range of frequencies, typically defined as 300 to 3000 hertz. Instead of dealing with all of the complexities with a signal such as voice, we can simplify it. In the frequency domain, we might talk about the 300 hertz signal all by itself. We can do all the calculations. We can see how the system would change the 300 hertz tone. We can then do all the calculations again at 3000 hertz. We can do those completely independent of each other. In fact, you'll often see me do this. I'll simply describe voice as a wedge of frequencies between 300 and 3000 hertz. With this simplification, we can run a calculation at 300 hertz. We can run it again at 3000 hertz. If it's good on both ends, we can have some confidence that the stuff inside will not be changed. This wedge of frequencies will become very important to us soon in our discussions of modulation. As a sidebar, everything we've talked about is applicable to machinery. We mean things such as gear mesh, vibration, or misalignment, oil whirl, and the condition of motors. All of these things can be described in the time and frequency domain. These concepts are important for preventative maintenance, where you can detect problems early. They're also important in military applications, where you're concerned about how much noise your machinery is making. As we end this discussion, I'd like to do a mind map of waveforms. Let's explore what we know and see if we can come up with some relationships. So we'll put waveforms here. We could talk about different types of waveforms. Voice. That's a rather complex one. Sinusoid, square, triangle. We can measure our waveforms. The things we measure are time, or time is an attribute that we measure, amplitude, and frequency. We measure using various instruments, such as the oscilloscope, the spec analyzer, the spectrograph. Our waveforms have a bandwidth. That was easy to measure in the frequency domain because you could just perform the calculation, right? It's just F2 minus F1. Things are a little bit more complicated in the time domain, but we can make some general statements. We can say that a sinusoid has small bandwidth. So we'll just use that as an arrow, so a low B. Whereas a square wave has a high bandwidth. In fact, we could talk about discontinuities. I haven't mentioned this yet, but if you have a discontinuity, for example, a lightning strike, right? A lightning strike in the time domain looks like that, right? Just a huge burst of energy in the time domain. That bolt of lightning, which appears so simple in the time domain, ends up in the frequency domain as having a nearly infinite frequency. So a spike in the time domain is all frequencies in the frequency domain. And I think that one's rather interesting. Anyway, the point I wanted to make is that these rising edges are problematic. We see these discontinuities in other places. For example, in power electronics, there is a device called a silicon-controlled rectifier, or a triac. And it might give you a waveform that looks like this. It basically takes a sinusoid and cuts it off. Anyway, you get this transition here, this rising edge. And you can see that that has a very large bandwidth. Now, it's not exactly a square wave, but you can already do some guesstimation here, and you can talk about the fundamental frequency, and you know darn well that there's going to be harmonics out here. Some of those may be odd, some of those may be even, but they're going to be there. So what looks like, or what would appear to be, say, a 60 hertz waveform, will have harmonics that extend way up, sometimes even into the radio frequency range. Anyway, we digress. Let's go back to this. So we have all of these things relating to waveforms. And now comes the missing piece, the piece that goes here. And that piece is modulation. Everything we've learned about waveforms is applicable to the concept of modulation. And that will be our next topic of conversation.